Golf Ball Simulator by Preston Lee, Jonah Johnson, and Shandu McAnady.
And here we have the golf club information. Our driver, which is meant for long range shootings, has a average distance of 183 yards, and its golf ball launch angle is 13 degrees, and the mass of the wedge is 0.18 kilograms. Our 7-iron club is meant for medium range, and its average distance is 140 yards, and the angle that the golf ball gets launched at is 39 degrees, and the wedge mass is 0.258 kilograms. Our lob wedge is meant for short range, and its average distance is 65 yards, and the angle at which the golf ball gets launched at is 61 degrees, and the mass of the wedge is 0.34 kilograms. The shaft length for all three is the same, which is 1.2192 meters. And at the very bottom, you see that we have a picture of each type of golf club. And the coefficient of restitution between golf ball and club is 0.83, and that's the max limit for golf. Most golf balls have a mass of 0.04593 kilograms. We also have to think about rolling friction and air resistance as it affects the golf ball. The dimples on the golf ball help increase spin when air resistance applied, which allows the ball to travel further. We also have to account for the resistance in the x and y direction, and when the golf ball has 150 dimples, the average surface area for the golf ball is 0.7166 meters squared. But for this problem, we will also be ignoring air resistance and spin. As you can see, we have two different images of what the machine looks like. When the golf club drops down, it's going to hit the golf ball. And depending on the type of club being used, we have three different trajectories that show the path that the golf ball is taking. Here we have the golf ball movement analysis, otherwise our projectile motion of the golf ball. The ball weighs 45.93 grams, or 0.04593 kilograms, which I mentioned in the second slide. The projectile motion in the x direction will be the force from the golf club, which is cosine, and the air resistance. Note again, we are not putting air resistance in our problem. And the y direction will be the sign of the force from the golf club and gravity. There will be an initial velocity from the club, which is stage 1, a midway velocity when the ball bounces once, which is stage 2, and a final velocity when the ball lands after bouncing, in which will come to a stop due to rolling friction, which is stage 3. Air resistance will be moving against the golf ball, slowing it down. The golf ball will be hit with the precise force needed to make the golf ball travel to the desired displacement. So here is how we set up our projectile motion equation. We have our equation to find distance, and these are all the symbols that we're going to be using for our equations. So as you can see, Vy is velocity in the y direction, Vx is velocity in the x direction. The equation for velocity in the y direction is v times sine theta, and velocity in the x direction is v times cos theta. And our velocity final symbol is Vf, and we have theta, which is the angle of the ball, and again, x is the distance in the x direction, y is the distance in the y direction, and g will equal gravity, and t will equal time.
All right, now that projectile motion for the ball is set up, we can dive into the equations and information. So we got our four equations for the velocity in the x direction, the velocity in the y direction, the displacement equation for the x direction, and the displacement equation for the y direction. We got our 7 knowns. We got both the displacement and angle for all three clubs, and gravity. And what we want to know are the velocities in the x and y direction, the overall velocity, and the time it takes for the ball to land.
As you can see with the projectile motion equations, knowns and unknowns, we are able to use EES in order to plug in all of our variables. As you can see, we have an output of final velocity, velocity in the y, velocity in the x, and time, all based on gravity, the angle of degree, theta, the distance the ball traveled, x, and the final state of the ball, y, which is 0.
How to explain the numbers that we got. Using the known values that we were given, we were able to calculate the initial and final velocity, the velocity in the x and y direction, and the total amount of time it takes for the ball to travel from the initial position to the final position, given that the ball travels on a straight line for all three clubs. With these velocities, we can now work backwards to find the needed velocity of the golf club before making contact with the ball in order to be able to achieve this velocity for the ball. It's a weird way to approach it, but mathematically, this is the easiest way.
Here we have the golf club movement analysis. Our simulator follows a simple pendulum path. We will be ignoring what happens to the golf club after it hits the ball, and we won't be including air resistance. The only thing that we need is the mass of the wedge, the length of the stick, the angle away from the ball, and the gravity acting on the pendulum. We will not be including the shape of the head of the club within our calculations just to make the problem simpler. To our right, we have the equation that shows the conservation of energy that applies to the pendulum motion, and we're using this equation because we won't be including air resistance.
We can now bring in our assumptions, equations, knowns, and unknowns that we'll be solving for. So we're going to be assuming the swing speed is constant and pendulum motion only adds to the overall velocity. And we're adding the gravitational velocity of the swing to the final velocity. So our equations, using the conservation of energy, we know that the potential energy at the top of the swing is going to be equal to the kinetic energy at the bottom of the swing. And then we got the equation for potential energy and the equation for kinetic energy. So we know the masses of all three clubs, the gravity, the length of the stick on the club, and the angle that we're going to be starting the swing from. What we want to solve for is kinetic energy, potential energy, and velocity.
As you can see, with the concept of conservation of energy and the potential and kinetic energy equations and our known values, we're able to use EES again to solve for our unknowns. With the given mass, gravity, height or length of the golf club, and the degree of which the golf club is angled above the ground, we're able to solve for the velocity that is added to the swing depending on the golf club. And as you can see, with our equations, comparing potential and kinetic energy, mass cancels out, giving the consistent additional velocity to each swing, being 4.89 meters per second.
Now we'll be talking about momentum transfer from the golf club to the golf ball. The moment the club and the ball make contact, the energy from the club gets transferred onto the ball, causing the ball to launch into the far distance with velocity that is carried onward from the wedge. The concept of linear momentum and work energy makes it easy for us to find the velocity of the ball. And to find the velocity of the pendulum at 90 degrees will give us the velocity of the ball. The length of the club will always stay the same, which is 1.2192 meters, but the mass will be changed based off which club you're using, and the final theta of each club will always be 90 degrees. The club also needs another force because gravity isn't enough to cause the initial velocity of the ball. Here we have the setup for the equation that we need to find the momentum transfer between the club and the golf ball. mc will equal the mass of the club, mb will equal the mass of the ball. Vci will equal velocity of the club initial, vbi will equal velocity of the ball initial, vcf will equal velocity of the club final, and vbf will equal velocity of the ball final. And COR, or coefficient of restitution, will equal vbf minus vcf all over vci minus vbi. And the conservation of momentum equation is the mass of the club times velocity of the club initial plus mass of the ball times velocity of the ball initial, which will all equal to mass of the club times velocity of the club final plus mass of the ball times velocity of the ball final.
Now that momentum transfer of the golf club swing to the golf ball is set up, we can quickly go into our known equations, our knowns, and the unknowns we want to solve for. So we got the equation for conservation momentum, which what we will be using, and the coefficient of restitution. So we know the mass and ball velocity of the driver, 7-iron, and lob wedge, the mass of the ball, the initial velocity of the ball, and the coefficient of restitution. What we want to solve for is the initial club velocity and the final club velocity.
As you can see, with conservation of momentum and the coefficient of restitution, we're able to solve for the velocity that results from the loss of energy as the ball is hit by the golf club. So with that, we were able to show in EES how to solve our problem. As you can see, we are now able to solve for the amount of velocity that the golf club had to have right before it made contact with the golf ball. This information, combined with the pendulum motion information, would give us our initial velocity that needs to be applied to the golf club as it's being swung downward toward the golf ball. But for our purposes, this is just the number that we choose to represent the velocity of the golf club.
So now that we know the velocity of the golf club swing, we can then start stage 2. So here we got the knowns and unknowns for bounce 1 and the resulting projectile motion. So we have our 6 equations, the coefficient of restitution, the velocities in the x and y direction, the displacements in the x and y axes, and for E, or another coefficient of restitution equation, obtained from a study we found, which is in our sources. The coefficient of restitution for impact of a golf ball on flat grass above 20 meters a second is 0.12, while below 20 meters a second, it's that complicated equation you see right there. Some important things to note about our numbers and equations are the angle of impact stays the same from initial hit to bounce hit because we are ignoring air resistance. And using the logic of bounces and retained energy, the leftover energy from the ball hitting the ground will be 12% because we have a coefficient of restitution of 0.12. So we know the coefficient of restitution, the initial ball velocity, and the angle of the driver, 7-iron, and lob wedge, the initial and final velocity for the ground, and gravity. What we want to find out is the final ball velocity, the final ball velocity in the y direction, and the overall velocity.
As you can see, we have combined both the bounce and projectile motion onto one slide as we wish to show the relationship between the two. Using EES, we were able to solve for the amount of energy lost, specifically in the y direction, which translates to the rest of the motion of the golf ball. So we solve for the y velocity resulting from the collision with the ground, being bounce 1, and then the resulting projectile motion that results from that bounce. So in this case, VBF from the collision is equal to Vy in the projectile motion. And the reason we did this was to solve for the total velocity and x velocity for each of the golf clubs.
Now that we know those numbers, we can then solve for the final collision with the ground before rolling. So we got both of our coefficient restitution equations, the velocities in the x and y direction equations, and the displacement in the x and y direction equations. We know the total velocity, the initial y velocity, and the angle of all 3 clubs, and the initial and final velocity of the ground. What we want to find out is the coefficient of restitution for each ball, the displacement, the final velocity of both the x and y direction, and for time.
We now want to solve for the energy lost when colliding with the ground for the last time. We will now neglect all velocity in the y when calculating for the ball rolling on the ground. Again, we use EES to show our work and do the calculations. As you can see, the first calculations are the collision with the ground for the second and final time. As you can see, yet again we calculate for the velocity in the y, which is VBF in this case, and we do so using a different coefficient of restitution, which requires the golf ball because the total velocity of the golf ball is less than 20, and so it's not a constant. With the velocity in the y calculated from the collision with the ground, we were able to use the projectile motion equations yet again, but instead of calculating for the total projectile motion of the system, we are now going to neglect the ball's y velocity, which means that it's not spending any time in the air, it didn't travel any distance yet, and there is no angle or any other component other than velocity in the x and the component of gravity, which will become relevant on the next few slides.
So what do all these numbers mean? Well, as you just saw, we were able to calculate the collision of the ball hitting the ground and the projectile motion of the ball resulting from the bounce off the ground, which is the velocity, displacement, and time. The collision of the ball hitting the ground the second time, which will be used when calculating how far the ball rolls after this collision, and the collision of the ball hitting the ground the second time, which we will use when calculating how far the ball will roll to a stop. And we were also able to calculate the collision of the ball hitting the ground the second time, which we will need for stage 3 in order to figure out how long it takes and how far the ball will go before coming to a complete stop, assuming that y velocity is ignored after this second bounce. So, what we know about stage 3, or the ball coming to a stop. We know the coefficient of rolling friction for grass, We're assuming that the coefficient of friction is constantly moving against the ball, and we're also assuming that it moves in a straight line. We'll be taking the velocity from the first bounce when it finishes, and friction will have a constant deceleration. We're also going to assume that the ball will not slip, and the grass will be treated as flat ground. So we got our equation to solve for the distance, the time, and the acceleration due to friction. We know the initial velocities for all three clubs, or ball swings, the final velocity, the coefficient of restitution, and gravity. We want to solve for the acceleration of the ball, the displacement, and the time it takes to stop.
Yet again, we choose to use EES to show how we did our calculations. And as you can see, we're able to calculate for the distance that the ball rolls on the ground before coming to a stop for each golf club.
So what do these numbers even mean? Well, given the ball was rolling on the ground, we were able to calculate how far and how long the ball rolled before stopping due to friction. So basically, we were able to calculate the distance the ball rolls before stopping, the time it takes to stop the ball, and the deceleration due to friction.
Here's a collection of all of our data. We have the velocity of the golf club at stage 0. We have the velocity of the golf ball, the distance the golf ball traveled, and the amount of time it took for the golf ball to travel that distance for stage 1. We have the velocity after the bounce of stage 2. We have the velocity, distance traveled, and time it took the ball to travel that distance for the projectile motion resulting from the bounce, which is the second part of stage 2. And we have stage 3, where the ball is rolling and comes to a stop. And we have the negative acceleration due to gravity, we have the total distance traveled for each ball, and the amount of time it took for the ball to stop rolling. And at the very end, we have the total distance the ball traveled, and the amount of time it took for the ball to travel that distance. As you can see, for the long driver, it traveled the farthest distance, and took the least amount of time. For the medium 7-iron, it traveled the second most amount of distance, which is expected, and actually took the most amount of time. And for the short lob wedge, it traveled the least amount of distance and took the second most time.
In conclusion, we have completed a semi-realistic simulation of a golf ball after being hit by a given golf club. Our simulation can allow for any type of golf club given the average distance the golf ball travels and the angle of the face of the club. Our simulation's answers, however, do not fully portray real life, as air resistance, spin, and the z direction are not accounted for.
The last thing that we wanted to talk about was whether our scenario was realistic or not, and a lot of that has to do with air resistance. Overall, our calculations replicated real life to the best of their ability with the initial parameters that we gave it. So our simulation is fairly accurate. The flaws in our calculation, however, have to do with the lack of air resistance, the fact that we didn't include rotation of the ball, which happens as it travels through the air and as it rolls on the ground, the fact that the ball would have bounced more than once before rolling and then coming to a stop, and the fact that the ball would have traveled in 3 dimensions. We treated it as X and Y. The ball is only staying on those 2 planes, whereas in a real-life golf swing, the ball is going to be traveling horizontally in 2 axes, meaning, say, X and Y, and then also vertically in a Z direction. So we did not include that in our calculations and in our theory about this scenario. And the last thing that we should address is the impact of air resistance further in detail, because air resistance would have played a huge difference in these calculations. So as you can see, the picture on the right depicts a rough idea of how air resistance works. So obviously there's the theoretical trajectory and the trajectory with air resistance. The trajectory with air resistance is much shorter, and the angle at which the ball would have made contact with the ground would have been much steeper. We calculated the theoretical trajectory, and so you can kind of picture the difference that it would have made. The ball wouldn't have traveled as far after it bounced, and it wouldn't have traveled as far in general from the initial hit as well. But other than that, I would say that the calculations that we've done so far have been fairly accurate with real-life calculations. I would say that air resistance does play a big role, but in our case, it isn't as great of an error. Here are a bunch of the sources that we used. We wanted to thank our professor, Ghosh, and thank you for listening.